Alright, welcome back to Let's Learn Algorithms. In the last video I did, we covered queues. So in this video I want to cover stacks, which are similar, and you'll see the two used sort of, not interchangeably, but you'll see the two used in similar types of problems. For example, whenever you've got graph theory, you use a stack to do a DFS and you use a queue to do a BFS. Aside from that, the algorithms really aren't that much different. It's just the data structure we use to store what we're going to look at next sort of dictates the order that we traverse the graph. So just to give you a quick idea of what this is, again, I'm going to leave full screen. This is a lot easier to explain whenever we're not looking at this in full screen, so I can actually move things around. So stacks are pretty much exactly what they sound like. They're like a stack of bricks, a stack of firewood, they're just a stack of things. And the way this works is whenever you take something and you want to put it into your stack, so pretend this empty square is our stack. Let's say we want to put the blue brick here. We'd stick it inside of our stack. We'd stick it on the top of our stack. So since our stack was empty, we just sort of created the stack. And then when we want to add a new block, say this red one, we stick it on the top of the stack. Same thing goes, we want to add the green one, we'd stick it on the top. And this is just how the stack generally works. You always put something on the top of the pile. So in code, we won't really necessarily have a top or a bottom, because programming doesn't really work that way. But whenever you're thinking about it mentally, think about putting things on the top of the stack and it'll make a lot more sense. So what makes a stack different from a queue is the fact that whenever you go to take things out of a stack, a queue, you would take things out of the front. So you put things in the back, you take things out of the front. In a stack, whenever you put things on the top, you also take things off of the top. So it's kind of like when you've got that stack of bricks outside or whatever, you don't go to the bottom one and try to pull that blue one here off the bottom. You instead go to the green block on top and you take it off whenever you need a block. So a stack is going to work that way. And I've got these two terms written here in the bottom left, FIFO and LIFO. They probably don't mean anything to you right now. So FIFO stands for first in, first out. So that's what that stands for. And a queue is first in, first out. What that means is the first thing stuck into the queue is going to be the first thing pulled out of the queue. A stack, on the other hand, is last in, first out. So what this means as the last item in is going to be the first one out. So if I just put this green block on top, that was the last item I put in, it's going to be the first one that I pull out whenever I pull something off of my stack. So that's really the big difference between, a stack and a queue is, whenever you're putting things on a stack, you take the most recently inserted item into the stack and that's what you work with next. The other thing that you'll sort of need to get used to is that stacks have different terminology than a queue. So a queue has, you can in-queue and de-queue things. A stack, on the other hand, has the terms push, pop, and peek. So peeking is, technically, I don't think it has to be a stack term, but it's something you'll see very common with stacks, so I just wanted to cover it here. Pushing means to add an item to the top of the stack. So you push this green block on top of the stack. Or popping means to remove an item from the top of the stack. So you'd pop this green block off the top of the stack. Peeking means to look at but not remove the top item. So if we were to peek at the stack right now, we would see that there's a red block on the top, but we wouldn't actually remove it from the top of the stack. The next thing we're going to cover is uses for a stack. So it's hard to go into too much details for uses for a stack, specifically because you kind of need to understand how a DFS or a BFS works to really appreciate the stack. But I can tell you that it is used for depth-first searches and some other graph theory algorithms like that. And it's also a very common thing to be used for processing arithmetic, specifically arithmetic that's in postfix format. So that probably doesn't mean anything to you. But I'll just tell you that it's kind of a way to evaluate arithmetic such that you can kind of take the parentheses and that sort of stuff and know which parts to evaluate first, but it's not in the normal format you're used to writing math. So most of you are probably used to writing math as like 1 plus 2 times 3 plus 4, something like this. Postfix is not this format. It's a little bit different format that's easier to sort of process for, at least in my opinion, whenever you're writing code. And a stack is useful for processing that type of format of arithmetic. But you don't need to worry about that right now. The easiest use case I can suggest is a DFS, and I have a video that actually covers a DFS. So If you check that out, you'll actually get to see how a stack works there. So the next thing we're going to do is cover how to implement a stack. We're going to be using Go, but realistically you could do this in pretty much any language. So just like the queue we covered, there's many different ways to implement a stack. You could use a linked list to sort of represent the items in your stack, slices, a fixed size array, and just like a queue, you can also set a maximum capacity and other things like that. We will not be doing anything crazy like this right now. We're just going to use a slice to make it simple, and there's not going to be any maximum capacity or anything like that for our stack. So just like the queue, I will say that adding and removing items from our stack, you might be like, oh, I can slightly optimize this in some ways if I use a fixed size array or something like that. For the most part, it's not worth concerning yourself with. Just using something that's simple and easy to use for now is going to be plenty, and I promise you this isn't like a super inefficient implementation of a stack. It's a reasonable one that should be fine for you to use moving forward. So just like in the queue that we did in the last video, a stack is going to have, the slice representation of our stack is going to have exactly the same number of items as are in our stack. So if the stack is empty, our slice will have a length of 0. If the stack has 4 items, our slice will have a length of 4. So exactly the same as the queue. And really the biggest difference between our stack implementation and our queue implementation is just going to come down to the pop and push functions. And even there, the push function where we add an item to our stack is probably going to be exactly the same as our in-queue function for a queue. Our pop function is going to be the one that actually changes, because instead of taking an item from the front of the queue, we instead take something from the top of the stack. So the last thing that I want to sort of mention is that we don't have a front and a back like we did with the queue. Instead, we have a bottom and a top. So whenever we look at this, I do want to mention that the bottom is going to be the lowest indice, and then, or the index, I guess, and then the top is going to be the highest index. So in this case, we've got 5 items in our stack. The 200 at the bottom is going to have the index 0, and then the 1 at the top is going to have the index of 4. So that's how we're planning on representing this in our code. Now you could change that if you really wanted to, but for our implementation that we're doing in this video, that's how we're going to look at things. All right, so let's do the coding. I'm going to go over here to my code. I've got this empty stack.go file, and in it we're going to write an integer stack. So first we need the type. So we're going to say type stack. It's going to have a struct as the underlying type, and inside of that we're going to have a slice of integers. All right, so this is pretty much the same as the queue that we wrote. Our stack is just going to be something that allows us to push, pop, and peek items inside of the stack, and it's going to handle actually handling the slice for us, so we don't have to really worry about it. Now, just like before, you might see implementations that have other variables like a top index or something like that, and it might keep track of things like that. For ours, we aren't going to do that because we can just resize the slice to sort of keep track of that for us. All right, so we need 3 functions. The first is push, where we take in an integer and we add it to the top of our stack. Add, okay, so this is push adds the integer provided to the top of the stack. All right, so now we also need another function. We'll do peek next. Peek returns the top item from the stack, but does not remove it from the stack. And lastly, we need our pop function. So this is pop removes and returns the top item from the stack. All right, so that's all we need. These 2 functions don't have return statements, so for now I'm going to put return 0. So let's start off with push. I think this is the easiest one, and it ends up being very similar to the queue code that we wrote, so it should be pretty simple. What we do here is we do s.slice equals append s.slice I. So the reason this works is if we go back to our slides, you'll notice that I'm saying the highest index is the top of our stack. And when we add items to a stack, we always add them to the top of the stack. So because of this, when we call append, it also adds items to the end of the slice, so at a higher index. So the two sort of work hand in hand and really work well for what we want to do. So we can just do s.slice equals append s.slice comma I. All right, so that's all we need for the push function. Moving on to the peek. This is where we just want to return the top item from the stack, and it does not actually remove it from the stack, but it just returns whatever value is there. So what we're going to do here is we're going to return s.slice, and we want the last item in the slice. So what this means is we need the length of the slice minus 1. So if I go back to our code here, you'll see that this stack here currently has 5 items. So the length would be 5. So 5 minus 1 is going to give us the index of 4, which is the top item in 0-based indexes. So that's why we're doing return s.slice, and then the index is, the length of the slice minus 1. So that's all we need for the peek function. We've got 2 down, just 1 to go. And when we get to the pop function, what's really nice here is that we've already written the peek function, so we can actually leverage that right now. So we don't really have to do a whole lot in our pop. We want to return the top item from the stack. So we'll say ret int equals s.peek. So instead of writing the code to get the top item, we can just peek it. So we have that value, and then we want to return it. So we're currently returning the top, the top item from our stack. All we need to do now is just change our slice so that it doesn't have the top item anymore. So s.slice equals s.slice. And from here, we're going to go from index 0, and then we're going to do length of s.slice minus 1. So we're doing the minus 1 here because we're telling it that we don't want to include the last item in our slice. So the item that we just peeked and that we want to pop off the top of our stack, we're saying that we don't want to include that one. So that line right here is what actually removes the top item. The first line is what gets it so that we can return it, and then we return that value. So that's everything we need to do for pop, peek, and for push. So the next thing we need to do is just sort of test this out, see how it works, make sure everything's good. So I'm just, again, going to use a main function. We could be writing tests to do this, but I don't want to spend a lot of time sort of doing test coverage. Instead, I'd just like to sort of show you this in action so you can see it. So we'll do it. Var s stack equals new stack. And then we're going to do s.push. We'll add 1, 2, 3. Actually, let's go back here. Let's add this example here. So add 200, 3, 44, 23, 1. So 200, 3, 44, 23, 1. All right, let's go ahead and format.println this and just sort of see what we have in our stack. And we're going to go run. Let me go ahead and clear my screen. Go run stack.go. And you can see here that we've got 200, 3. Do we want? Yeah, we want 200. So we got 200, 3, 44, 23, and 1. So the left-hand side in this representation is the bottom of our stack, and the right-hand side is the top of our stack. So lowest index is the bottom, highest index is the top. If we go back to our example here, you can see that lowest index is the bottom, highest index is the top. That's what we wanted. So we can also make this print out a little bit prettier. I did this before in the Q one. We can just write a string function and return format.sprint s.slice. So this will just basically say that however it normally prints out a slice is how we want to print out our stack. That just gets rid of some of the, the outer parts of this. So we just get something that looks more like an array. Okay, so our push is working. Next thing we want to do is we want to make sure that our peek and our pops are working. So we'll go ahead here and we'll do format.println. And technically it's fumpt.println. I just always call it format. So we're going to peek the first item, and then we're going to pop the first item. Now both of these should return the same thing, but when we call it the second time, the second peek should give us 23, and the second pop should give us 23, because pop should be removing it, whereas peek isn't. So let's just go ahead and run it, and it looks like something's wrong. So you can see here that this pop apparently didn't remove an item from our slice or something like that. So we need to figure out why that's the case and sort of go from there. So let's print line S and just sort of see what happens. Apparently I saved a different version of the code. So our code is working correctly. I just only called pop and peek once there. I didn't call them both twice. Okay, so the second run through, you can see that we create the stack, then we peek the first item, it's a 1, we pop it, it's a 1. Then we look at the stack again, we've got 203, 44, 23. Peek the first item, it's a 23. Pop it, it's a 23. So let's get rid of these. The peek and the pops are working, and we also know that pop uses peek. So we don't really have to check both right this second. I'm just going to stick with the pops, and we're going to let's do another pop, and then let's add another item. Let's do 99. So then let's print line here and just print out the entire thing. Then let's print out s.pop. So the reason I wanted to do this 99 here was I wanted to show you that we've got our stack here. We pop the 1, and then we have our stack again. We pop 23, then we pop 44, so those are both in the order we expected. And then we go down here to the stack, and at this point we push this 99. So this 99 gets put on top of the stack, and then I just wanted to show you that if we pop again, the 99 is what comes pulled off the stack first. All right, so everything is working correctly. The last thing I'm going to show you is something that I don't think I've mentioned yet, and it's the fact that we don't have any sort of error checking with pop and peek to make sure that there's actually items left in our stack. So if I pop too many times and run our code, you'll see here that we get this index out of range error. So what's happening here is that we're trying to access something in our stack, so we're trying to access something in the slice specifically that isn't there. And the reason it's not there is because we've popped all the items off of our stack and we're getting an error there. Now, if you wanted to fix this, one of the ways to do it is to change this return type from int to int comma error. And then you can say, if len of s.slice is equals 0, return, say 0 errors.new, no items left in the stack. Something like that. So you could do something along those lines, and then down here you could instead do this and pass nil for the error. We're not going to do that specifically because for the most part, whenever I'm using a stack, it's kind of like using a slice. I expect the end user to sort of have some sort of checks in place. But one of the ways to do that is to actually go ahead and change this all and to add a size function. So we return the length of s.slice, and now you can use that size function just to sort of verify that, can I actually pop? So it's kind of like a slice. People can freely access invalid indexes, and the code will panic. It doesn't return an error when that happens. So whenever I write my stacks, I tend to sort of treat them the same way, where you're supposed to write some code that uses this correctly, and if not, that's kind of on you. All right, so I mentioned this before with the queue. I guess I can talk about it very briefly here as well. Generics are something that don't exist in Go. So if you want to create stacks for different types, you'll have to actually create a different implementation for each type, or you'll have to change this to be a slice of interfaces and change all of your functions like push and peek to return and accept interfaces. Now, I know this doesn't sound ideal, but I promise you it's really not that bad when you get the hang of it. It just ends up being a little bit more code up front, but it ends up being very easy to read the code, especially for beginners and stuff like people like that who aren't intimately familiar with how generics work, because they can be very, very confusing. I've seen tons and tons of people get confused with generics in Java, and despite them being very valuable, they are confusing. If you enjoyed this video and you want to check out some of my other work, you can find pretty much everything that I work on at www.calhoun.io. And if you join my mailing list, I will send you an email probably about once a week that just sort of lets you know what new stuff I'm publishing. And you can just keep in touch with new content that I'm creating. I also have a course that teaches web development with Go. You can find that at www.usegolang.com. So if you could check those two out, I'd really appreciate it.